I'm gonna pick the classical example of a pendulum. All right, so I'm just gonna draw that right here really quick. So this is a pendulum. All right, so this is the string. This is some mass. This pendulum has length L. The mass is M. And let's see. We're gonna define, and let me just redraw this hinge real quick. So it's horizontal like that. Okay, there we go. And this is just to represent some surface that is fixed. And what I want to do here in this example is to find the position of that mass. More than finding it, I would say actually represent or determined. I would say determine. So to determine the position of this mass M, well, again, we need to define a coordinate system that is attached to a reference frame. For the simplicity of this video, I'm just going to talk about a coordinate system. So we need to define that coordinate system somewhere and somehow. And if you watch my previous video on that, you'll see that we need to have that coordinate system fixed somewhere, but it is not a requirement. Although at the end of the day, when you want to apply physical laws like Newton's laws, well, you need a fixed inertial coordinate system to apply those laws. But you can also have moving coordinate systems. But in this case, well, let's talk about the inertial frame that we're going to use. All right, so I can define that position, the position of this pendulum with respect to something. So I need to define a coordinate system, and you can define it however you want. You can have that X and Y system right here, or you can place it maybe here at the bottom, and in that case might be something like this, or you can define it even like this. But I would say for the convenience of this example, we could do X downwards, and let's do Y to the right, and see that I'm placing it right at the hinge. I could have placed it anywhere else, but it's convenient to do it that way because your expression for the position will be simpler, or relatively simpler. Because see, for example, if you would have taken this reference frame right here, this coordinate system right here, what you need to do might be convenient to do some position reference to the hinge, and then from the hinge go to the mass. And in that case, you will need to move somewhat in Y, in X, but you will need two vectors to represent the position of the pendulum, while if you choose only this reference frame, you only need one vector, which will be along the string of this pendulum. So let me remove these other frames right here just to avoid confusion. And let's then define the position of the pendulum. And again, this is a vector quantity, so we will need a magnitude, and we will need the direction of it. All right, so let's just do this real quick so we keep this video short. So I'm just gonna draw those lines to complete that triangle that forms there, so that facilitates writing the position of the pendulum. So let's see. The position of the pendulum, I'm gonna represent it with this P, and I'm gonna draw this line here just to say this is a vector quantity. Okay, right. So the position of the pendulum, let's see. We need to express this position in terms of X and Y, which are vectors themselves. The position of the pendulum, let's decompose it into the X coordinate and the Y coordinate. So in X, well, I'm gonna define this angle theta, so we can decompose the length of the pendulum along X and then Y. So for the X direction, I'm just gonna call it the x-axis, because, and this is a vector, right? So I'm gonna put that line over here and over here. All right, so in x and in y we'll have components. So for the x component, we will have something like L. Cosine of theta, that would be this side over here. And then we will need this side of the triangle over here. That would be L sine of theta. All right, at this point, we have the position of that pendulum expressed in that white frame. So let me just rewrite this to make it a little bit cleaner. And at this point, we have the position of the pendulum in that coordinate system. Now, it gets very interesting if you define a different frame and then try to write the position of the pendulum in the other frame. Say, let me pick another color real quick. So what if you do, instead of choosing x down, what if you would have done something like y down here, and then what if you do x to the left? If you do that, can you still write the position of the pendulum? And the answer is yes, we can. Indeed, in fact, we can just write it in any other frame. You can define any frame you want. You can define any coordinate system you want, like what we discussed in the beginning, and you can simply, and let me just call this option 2, and then this will be, say, option 3. You have infinite options here, and you can just write this P in any frame. And it gets interesting then, because, well, now you have infinite ways to express the position or that velocity or the force or the torque or any of the vector quantities that you're working with. And now it gets a little bit further, because what if it is convenient to have not one but maybe 2 reference frames? Can I combine representations? Can I combine different frames? And the answer is yes. So let's see. Let's just write that here for the record. So to show you this, let's modify the pendulum example a little bit more. So we have some guide here. We have this is a guide, a channel, where we have a small cart right here, and then we have, actually, let me just draw it more over here in the middle. So we have this little cart, and then that cart is actually carrying that pendulum. And now we have that cart that can move back and forth, and that it carries that pendulum. So now, if you want to define the position of the pendulum and the cart, possibly, well, you need a coordinate system again. For me, I think it is easy just to have that origin right here, and then have x down, and then we have y to the left. So it will be x, and this will be y. Well, we know what the expression for the pendulum is with respect to the hinge, and so I'm just going to grab that from here. Just gonna paste it here. So we know that this is with respect to the hinge. This is from the hinge, right? So no, that's from the hinge. And now, because, well, we want the overall position of the system, including the cart, well, now we also need to know where the cart is. And once we know where the cart is, and that quantity will be this distance, right? So if we know where the cart is, then we simply add at the end the position of the pendulum with respect to the hinge. So we want to know where that hinge is. That hinge is right here. This it's on the cart. And well, this is a simple enough example, and we can just really easily see that this distance, which has this direction y, will be, well, we can just call that d. It's a distance d along y. So again, notice that d would be the magnitude and y would be the direction for this position. All right, so if we write the position of the cart, so this is the position of the pendulum, position of M. So now let's just define that position of the cart. Let's call position of the cart PC. And that's very simple. It would be D, that's the magnitude. And then the direction is Y. All right, now we can add add everything, right? I'm just gonna write that over here, PM, the position of the mass. So the position, the position of the mass with respect to the hinge. I'm just gonna use that notation over here. So this is the position of the mass with respect to the hinge. That's what we're gonna call it. And so this is the position of the cart. All right. So the position of the mass with respect to the inertial frame, the inertial coordinate system. So inertial frame. Let's call it the position of the mass in the inertial frame. And this is a vector, so I put that small line over there. It would be just adding the two vectors. So we need to go, and we need to go from the origin all the way to the hinge, and that corresponds to travel a d distance along y. And once we are at the hinge, then we can travel along the pendulum, or like we did before. Once we are at the hinge, we go down, and then we go to the right. And to go down, we'll remember from the previous sketch, to go down, it was a component in x, which corresponds to the first term, and then we move to the right, which corresponds to this other term, which we have written here. So we go down, and then we go to the right. So we just write it right here. So it would be, again, we're at the hinge because of this term, and now we want to go down and then to the right. So we write those two components. So we move down along x, and then we move. See, this term is right here, and then we move to the right. So we're gonna write that term over here. This would be the position of the mass with respect to that inertial frame. So you see, at the end of the day, we need to keep track of magnitudes and directions. And the same concept applies to velocities and accelerations and force and all these vector quantities. You need to keep track of the magnitude and the direction so you can do operations with them and do the modeling that we're trying to do. Because at the end of the day, what we want to do is study the motion of the system or the dynamics of the system in a more general way. So we're going to end this video here, and I just want to point out that at this point, we only have the position of this mass, and we haven't talked about any dynamics. We're talking about kinematics here, only kinematics. We haven't talked about forces that make this card move, but notice that once you have your position, well, you can start taking derivatives of this to get the velocity, and you can take another derivative to get an acceleration, and then write your Newton's law. Or maybe you are dealing with torques, and you need, instead of the angular position, well, you need to take the second derivative of that so you can get the angular acceleration, and then write your Euler equations. And you will do all that taking care of all these vector quantities in a proper way if you want to get the right results. And we'll talk about those things in the next video.